The Lewis model that we've been talking about is an oversimplification. It's an oversimplification and doesn't apply to everything. There are more advanced theories that employ quantum mechanics. And we're going to look at two of these in a qualitative manner, meaning we're not going to get into the crazy math involved in them. Modern quantitative approaches are amazingly accurate. They can predict bond length and strength, geometries, dipole moments, all kinds of cool stuff. But it involves some pretty hairy math, and we don't need to go into it that far. So we're going to talk about it in a qualitative manner. So we're not going to do a lot of math with this. So we've learned that electrons reside in quantum mechanical orbitals that are localized on individual atoms. We talked about this when we talked about quantum mechanics. And these in an atom are given the letters S, P, D, and F. Those refer to the different subshells in a principal energy level of the quantum mechanical model. That's what they do when they are atoms, but when we get a molecule, these atomic orbitals can hybridize, they can blend together, so that when two atoms approach each other, the electrons and nucleus of one atom interact with those of another. And valence bond theory is looking at the energy changes that result from these interactions. And what we find is a chemical bond will form if the energy of the system is lowered by the interaction. So if energy is lowered, the bond forms. If energy is not lowered, the bond does not form. So here's an illustration of hydrogen atoms approaching each other. Here they're very, very close, and here they're far apart. When they're farther apart, the energy is slightly negative. Does that mean they're attracted to each other or repelled by each other? Negative energy. They're slightly attracted. Yeah, if you just keep guessing, you'll come out right eventually.
Like energy repelled.
Like charges repel. When these two atoms, which overall they are each neutral, the attraction comes between the electrons of one atom and the nucleus of the other atom. So it gets a little difficult to think about sometimes. But these two atoms, when they're fairly distant apart, the energy is slightly negative. They're slightly attracted, but it's close to zero. As they get closer together, the energy decreases. It becomes more negative. And so there's more attraction, which draws them closer. It comes to a minimum when they are a particular distance apart. If they continue to get closer, the energy will increase and eventually become positive and push them away from each other. So it's a little bit like a ball rolling down the hill, right? Its potential energy gets lower and lower and lower, but it's got some momentum it carries up, and it kind of goes back, and it's going to end up at the bottom. And so these two atoms are going to be most stable when they are this distance apart. What is that distance? It's a distance that allows their 1s orbitals to overlap substantially without having too much repulsion between the nuclei. And so this distance where the molecule now is most stable is the bond length of the hydrogen molecule. And the energy here is the bond energy. The interaction energy is negative when we have interacting atomic orbitals that have electrons that can spin pair, orient with opposing spins. Usually those electrons are going to come from two half-filled orbitals. Because what's the problem with two electrons being close to each other? It's what Will said earlier. They're both negative, like charges repel each other. Well, for that matter, how can electrons share the same orbital? We talked about spin pairing, right? And when electrons have opposite spin, then they can be together without getting on each other's nerves. So when these electrons overlap, when those orbitals overlap, the electrons in them need to be able to spin pair. So usually it comes from half-filled orbitals, but sometimes two electrons come from a filled orbital and they will overlap with an empty orbital of the other atom. That has a special name. That's called a coordinate covalent bond, and that's where one atom is providing both of the electrons. That's like, giving donations. You've got a poor relative or something, and they can't pitch in their fair share. So you'll pitch in for them. So coordinate covalent bond, both of the electrons in the bond come from the same atom. When those two atoms that have the half-filled orbitals approach each other, the orbitals overlap, and the electrons will align with opposite spins. And so then they can occupy that overlapping orbital just like electrons do in the atomic orbitals. So we understand that valence electrons in atoms reside in quantum mechanical molecules. The chemical bond comes from the overlap of two half-filled orbitals with spin pairing. So there's going to be two electrons in a bond. And the geometry of those overlapping orbitals is what determines the shape of the molecule. Any questions yet? Well, let's look at how this happens. What if we look at, what is this? This is dihydrogen sulfide. So we have two hydrogen atoms and one sulfur atom. And here we have orbital diagrams for the three different atoms. The hydrogens are easy. They each have one electron in the 1s shell, 1s orbital. And s, we're looking only at its valence electrons. Its valence configuration is 3s2, 3p4. And so this, we would look at this orbital diagram and predict that this hydrogen 1s orbital would overlap with one of these 3p orbitals, and that the other hydrogen's 1s orbital would overlap with the other. And here's an illustration of that. Here we've got these, they look like red balloons. This is 1p orbital. That's the one that's got the pair of electrons in it. And here's another p orbital that had one electron from the sulfur. Now it overlaps with the hydrogen, and so we have a pair of electrons there, and that's forming a bond. And then perpendicular to those two, we have the third p orbital, which had one electron from sulfur and has one from hydrogen, and they're overlapping. What is the predicted bond angle here? 90 degrees, because those p orbitals are aligned perpendicular to each other, and the angles are 90 degrees. But it doesn't actually have a 90 degree angle. The actual angle is 92. And VSEPR theory, if we look at VSEPR theory, which we just learned how to do, we would end up with something like this. And we learned that we count the electron groups, 1, 2, 3, 4, tetrahedral electron geometry. What's the angle for that? It's about 109.5, but then we've got two lone pairs, and so we predict that the angle is less than 109.5. But the actual angle is 92. So neither of these is really giving us a good explanation for the geometry of dihydrogen sulfide. Let's look at methane. Well, here's the orbital diagram for carbon. There's a filled 2s orbital, and there are two half-filled 2p orbitals. And here's hydrogen with a 1s half-filled orbital. So we could imagine that these guys are going to overlap. And so we've got overlap here. And then there's one more electron. So that would be like another hydrogen atom, right? And that could overlap with this one. You see what I'm doing? Taking half-filled orbitals and overlapping them and seeing what happens. So here's one orbital overlapping with hydrogen. Here's another one. Where's the third p orbital? There's 3 of them, right? Where's this third one? It's empty. So the prediction by doing that would be something like this. This is even worse than dihydrogen sulfide, right? This idea of just overlapping half-filled orbitals gave us an better than VSEPR theory for dihydrogen sulfide, but this isn't good. Because not only is the bond angle wrong, but the number of hydrogen atoms is wrong. In reality, we observe there are 4 hydrogens. It has a tetrahedral geometry with 109.5 angle. So obviously something's missing. We need an additional concept. Well, the orbitals in a molecule are not necessarily the same as orbitals in an atom. So we're familiar with the word hybrid, right? How do you hear hybrid in everyday life? Hybrid cars. What makes it a hybrid car? It runs on both electricity and gasoline. It's a combination of 2 different things, right? It's not either one, it's a combination. What's another thing that gets hybridized? Think biology or botany. Plants, right? You can hybridize plants and come up with a fruit tree that has different properties than either of the parents did. So hybridization, we're familiar with the idea. In chemistry, this is a mathematical procedure in which we take the standard atomic orbitals and we kind of mash them together, average them in a fancy way, and we get hybrid orbitals. So they come from the atomic orbitals, but they're not the same anymore. And doing this is going to cause us to get a better correlation with the actual distribution of electrons in molecules. We still have these electrons being localized on the atoms, and the orbitals are still localized on atoms, but they're going to have different shapes and energies than your standard orbitals do. So we hybridize the orbitals to minimize the energy of the molecule, and that is done by maximizing the orbital overlap. The more overlap of those orbitals, the more stable the molecule is. A more stable molecule has a lower energy. And the hybrid orbitals give us better overlap because the electron probability density, instead of being uniformly distributed around the atom, is more directional. It's more on one side of the atom. And hybridization requires energy. It doesn't just happen on its own. It's only going to happen if you get an energy payback from forming bonds with hybrid orbitals. If the payback is big enough, then the investment of energy is made. So what we're going to do is we're just going to look at interior atoms. We're not going to look at the atoms on the outside of the molecule, like hydrogen. We're just going to look at molecules that are like the central atom. And we know that atoms that form more bonds are more likely to hybridize. So this is not a horrendous assumption, but it makes everything just a little easier to deal with. And we're all for that, right? So just some general ideas. The number of standard orbitals added together always equals the number of hybrid orbitals. If you hybridize 3 orbitals, you end up with 3 hybrid orbitals. If you hybridize 4 orbitals, you get 4 hybrid orbitals. So you always end up with the same number of orbitals. And the particular combination is going to determine the shape and the energies of these orbitals. So if you've got one s orbital and one p orbital, it's going to have a different orientation, a different shape, a different energy than if you mix one s orbital with 3 p orbitals. And that makes sense. And the type of hybridization that actually happens is the one that gives the lowest overall energy. So there's calculations that can be done to do this, and those thankfully are beyond the scope of this class. If you're interested in those, either as a junior or senior as a chemistry major, you'll take a class called physical chemistry, and you'll learn all about that kind of stuff. So we're going to use VSEPR theory to help us predict what the hybridization is. So let's look at methane. Methane is CH4. So here are the standard atomic orbitals for carbon. The 2s orbital is lower in energy than the 2p orbitals, and so when it fills, we put 2 electrons in the 2s orbital and 1 each in the 2p orbitals. Well, hybridization takes all 4 of these orbitals and mashes them together and cuts them back into 4. We still end up with 4 orbitals, but these are now hybrids. They're an average of these 3. And so the energy of these guys is going to be between the energy of the s and the p orbitals. And all 4 of them are going to be the same. And we call them sp3 hybrid orbitals because they come from 1 s orbital and 3 p orbitals. sp3. So when we say the 4 hybrid orbitals are degenerate, that means they have the same energy. So what does that end up looking like? Well, here's an s orbital. There's one of the p's, another one, and there's the third one. You take all of those together and average them, basically, and you end up with these 4. Now, this looks a lot more like a turkey drumstick, doesn't it? You get 4 equal shapes. They're all the same shape. And they're going to be oriented in space to give each other as much room as possible. There's 4 of them. How do 4 things spread out in 3-dimensional space? What shape? We learned on Tuesday. Tetrahedron, right? So these are going to point to the corners of a tetrahedron, 1 to each corner. They do have a node, and so there are 2 lobes. One of them is much larger than the others. There's 2 lobes, one is larger than the other. When we draw them all together like this, we usually ignore this little lobe on the other side. But if you look at this one compared with, say, this one, when this one overlaps with an s orbital, maybe, well, I guess the s orbital's blue. I should keep it blue. If this orbital overlaps with an s, it can't overlap as much as one of these can. You see that? Because this end is bigger and fatter than this one. And it's directional. More of it is on one side, and only a little bit is on the far side. I loved the far side. Any questions about the sp3 hybrid orbitals? So if we draw an orbital diagram for this, we're going to draw 4 boxes together. 1, 2, 3, 4, because we took 4 orbitals and we averaged them. Carbon has 4 electrons in its valence shell, and so they can fit in here, 1 in each box with parallel spin, and that's Hund's rule. So here we have, in purple, those 4 hybrid orbitals. Each of them can overlap with the s orbital of a hydrogen atom. And we get a tetrahedral geometry, and we get a molecular formula of CH4, and everything agrees with experimental observation. And it's just awesome when this happens. And thank you, guy in the hall, for saying, woo, just at the right time. Hybrid orbitals can accommodate a lone pair. So for nitrogen, when nitrogen makes a hybrid orbital out of sp, makes an sp3 hybrid orbital, it's going to have one electron in each of these and a lone pair up here. Let's draw the orbital diagram. Because how many valence electrons does nitrogen have? 5, right? So go 1, 2, 3, 4, 5. This is sp3. So one of these is going to have a lone pair in it, that's this guy up here, and then 3 of them are going to be half filled, have 1 electron, and that can overlap with hydrogen and form a bond. We've got this tetrahedral geometry, this is lone pair, and so when we look at how this works out, we end up with what we expected from Lewis theory. But this lone pair is going to take up a little bit of extra space, and so it's going to cause these guys to squeeze together a little bit. When we've got a lone pair like this, the atom is not as likely to hybridize as when it doesn't have a lone pair. And so the hybridization is not 100% complete. And so this guy's going to retain a little bit more of the individual character than these 3 guys are. We can also hybridize 1s and 2p orbitals. So here again, electron configuration of 2s and 2p. There's 3 of them here. Here we're just taking the s and 2 of the p's and averaging them. This p over here remains unhybridized and unchanged. And these guys will be degenerate. They will be between the energy of the s and the p. And they're called sp2 hybrid orbitals because there's 1s and 2 p's. And so this unhybridized p orbital is left over. So now we're taking the s and 2 p's and we're mashing them together because these are all complicated mathematical functions, and so you can average them together and come up with another mathematical function that you can graph using a computer. And so this is what you end up with. You end up with 3 degenerate orbitals. They have a very similar shape. They've got a small lobe and a large lobe and a node at the nucleus. But 3 will arrange themselves in a trigonal planar geometry. And when we draw them all together, we tend to not draw that little lobe because it gets too complicated. It's there. We just don't draw it. Yeah. It's little, it's not as important. So let's look at H2CO. This molecule has sp2 hybrid orbitals. So the carbon can form 4 bonds. It's going to form 2 with hydrogen and 2 with oxygen. And that unhybridized p orbital is going to overlap with a p orbital of the oxygen. So here are the original unhybridized orbitals, and here's carbon, and it's going to hybridize, and you're going to have 3 sp2 orbitals and 1 unhybridized p orbital. Each of these will have 1 electron in it, and then it can overlap with 4 different things. Isn't that pretty? This is like balloon art day without actual balloons. So here's carbon, and the purple balloons here, they're not really balloons. They sure look like balloons though, don't they? The purple orbitals are the sp2 hybrid orbitals. There's 3 degenerate orbitals. They arrange themselves in that trigonal planar geometry. This one overlaps with hydrogen. This one overlaps with hydrogen. This one overlaps with oxygen. Let's just go back real quick. What's oxygen got going on here? It's got a full 2s and 2p orbitals. One of them is full. It's got 2 that could overlap. Remember, this is not a central atom in this molecule. We're going to ignore any hybridization that might occur with that one, just because we can. So this overlaps with one of the p orbitals for oxygen. And the double bond comes about from the unhybridized orbital of this carbon and an unhybridized orbital of the oxygen overlapping side to side. And that's what forms the second bond of the double bond. Now, does that look like a triple bond to anyone? It kind of looks like there's 1, 2, 3 things going on there, right? But remember, these orbitals have phases. And there's a positive phase and a negative phase. And so, you know, that squirrely electron pair is only going to be in one side or the other at a time. So it's not resonance, it's wave-particle duality of electrons. So we have one orbital here with one electron in it, overlapping with one orbital here with one electron in it. It overlaps here and it overlaps there, but that is one bond. The other bond is this overlap end-to-end between this sp2 hybrid and the unhybridized p orbital. You may have to recognize this, yes. It'll get better as we deal with it more. So this sort of a bond is called a sigma bond. It looks like an O with a little wing or something, maybe a cowlick. So that's an end-to-end overlap. Those are sigma bonds. Sigma bonds are symmetrical around the bond axis. So the bond axis would be from this nucleus to this nucleus. Let's draw that maybe in bright yellow. There's the bond axis. This bond is symmetrical around this axis. This bond is not. There's a piece up here and there's a piece down there. So that's a sigma orbital and this is a pi orbital. I'm sorry, pi orbital. Putting the wrong thing. Pi orbitals overlap side to side and sigma overlap end to end. So the pi bond happens when we get this side-by-side overlap. So we've got this half-filled orbital and this half-filled orbital, and they overlap side to side. The electrons occupy both lobes, but it's one orbital. It's one bond. The sigma is an end-to-end. So you can have a p orbital overlapping with the end of a p orbital, and you'll get a sigma bond. Or you can have a hybrid orbital overlapping with an unhybridized orbital. That's a sigma bond, end to end. It is kind of crazy. So, of course, we have to have some notation, some shorthand to talk about what these guys are. So this is that same molecule that we were looking at earlier. And we can describe each of these bonds. What kind of a bond is this, pi or sigma? Sigma, because it's the end of this hybrid orbital that's overlapping with the s orbital of hydrogen. The s orbital can't really do a side-to-side. It just overlaps with the end of somebody else. So this is a sigma orbital, and we can indicate that from the carbon has an sp2 orbital that's overlapping with the hydrogen's s orbital. And so both of these are the same. An sp2 from the carbon overlapping with an s orbital of the hydrogen. And then this one is also sigma because it's end-to-end. Here again we have carbon with an sp2 orbital, but the oxygen is using just a plain p orbital. So this is C sp2 OP. And this is the pi bond, and that's overlap side to side between carbon's unhybridized p orbital and oxygen's unhybridized p orbital. Any questions? Yes?
I'm really lost.
You're already lost. I'm not surprised.
Where's the sp2 coming from?
Where's the sp2 coming from? That's a good question. I'm sure someone else is thinking that as well. Let's go back. Okay, so we're okay with these guys, right? We learned how to do that a while ago. So here we've got carbon, and it has two half-filled orbitals.
Yeah.
So we would predict that it would form 2 bonds, but it doesn't. It actually forms 4 bonds. How does it do that? Well, it moves one of these electrons up to a higher orbital. And we saw that just moving it up and keeping these same shapes doesn't explain actual observations. So what happens is this electron moves up here, 3 of these hybridize, and the 4th one does not. Now, maybe the question you're thinking is, why? Why would it do that? Because it's a lower energy situation than if they all hybridize. It requires energy to hybridize, and the more orbitals that you hybridize, the more energy it takes. If you don't get enough energy back when you make the bonds, it's not worth it. And so in this situation, it isn't worth it to hybridize that last p orbital. We just leave him as is. We're not going to, we're not going to modernize him. We're not going to update him, remodel him. We're going to leave him alone. We're just going to pay attention to these other 3. So these 3 get hybridized, and that one does not.
Okay.
Does that help?
Yeah, it does.
And carbon can do different things when it forms different molecules. It doesn't always do the same thing. And that is a bit hard to grasp. So I don't want to lose the whole class here, okay? Because it's not going to we're not just almost done. We have some more to do. So if you're lost right now, ask me questions. Let's get it straightened out. We got Juan on board, so anybody else? I'll just talk to him. Yes?
Okay, well, let's start from the beginning.
Start from the beginning?
All right, why do electrons overlap? Why do these orbitals overlap?
Why do they overlap in the first place? Well, that's a good question. So let's go back. We're going back to the very beginning, almost the very beginning, to this guy. So there's attraction between these 2 atoms. As they get closer together, the attraction grows. It's an attraction between electrons that get shared and the nuclei. It's not attraction between the nuclei. The nuclei repel each other. And when these guys get too close, it's like, oh no, I liked you at an arm's length, but now that I'm too close to you, you don't smell very good. Back off, right? You don't want to get too close to somebody. And so this isn't a good situation. But there's this optimal spacing where we have a maximum amount of attraction and a minimum amount of repulsion. And the reason that the 2 electrons can be together there in the middle and attract both of the nuclei is because if they pair up, they can coexist in the same orbital. If they're not paired, they will not stay in the same orbital because they will repel each other. Did that help at all? A little bit.
Okay. Why, we're the same question earlier, Professor Juan. Why don't they distribute like the electrons in the orbitals? Why don't they distribute on the basis of spin? The other ones?
Well, the spin can, my understanding is the spin can change. They can flip.
Because it was like on the sp3 orbital,
Mm-hmm.
for example, we had a 2s orbital. Sort of like that. Yeah.
But like this one? No, maybe. Yeah, that one works right there.
Yes.
So here we had 1 electron that was spin down,
Yeah.
and now we have all 4 spin up.
Right.
Right? Why? He flipped.
She just flipped.
He flipped. He underwent a spin change operation. I don't know.
What causes the nodes in the orbital?
What causes the nodes in the orbitals? Okay, that's from a previous chapter. Right. That had to do with the radial distribution function combined with the other function that I can't remember the name of. Because as you get too close to the nucleus, if the electron was just attracted to the nucleus, then all the electrons would fall into the nucleus, right? And so there's like this no man's land around the nucleus where the electrons are almost never found. Not to say that they couldn't be, because anything's possible with an electron, pretty much. But they're not found there in the middle. And we had some graphs that were some really steep peaks and some shallow ones. And it comes down to very complicated math. And there is a great explanation for it. I can't give it to you right now.
It's mainly based off that graph.
Yeah, it has to do with probabilities and radial distribution and hairy math.
And then can we look at slide 57?
Yes, we absolutely can look at slide. These are great questions. You should do this more often. Okay. If we have orbitals with lobes, these could be p orbitals, they could be sp3, sp2, any lobe-shaped orbital that overlaps at the end. That's called a sigma bond. So let's imagine that this is the axis of the bond. We're looking from this nucleus to that nucleus. And what we're going to see when these guys overlap is that it's spherical. Right? It's spherical, this part. If we're looking at it from this direction, we see a sphere. So sphere, sigma, symmetrical. This is a sigma bond, an end-on view of a sigma bond. The pi bond is when you have two of these orbitals that are parallel to each other and they overlap side to side. And then you get something like this. And if we looked at this down the bond angle, we'd see something more like this. Where the electron density is up here and down here. This is not symmetrical around this yellow spot. Does that help?
It depends mostly on the orientation.
It depends on the orientation, yeah. See, the thing is, if you have both of these orbitals on the same atom, they can't both overlap end to end with the orbitals on a single other atom, right?
And you said that they only bond through the ends?
The sigma bonds are through the ends. So if we have both of these on the same two atoms and we're trying to do a double bond, well, we can get, I don't know how to draw this. We can get end-to-end overlap with these guys. But these guys, they're not flexible. We can't get end-to-end overlap, but we can get side-to-side overlap. Okay? Does that help? Anybody else? The questions are good. He asked them all. Yeah, he's a good question asker. So we can label them. And this helps us, the valence bond theory helps us to understand in more depth than the Lewis model. Lewis model, we were sharing valence electrons and we put two electrons and another two electrons to make a double bond so that everybody could get an octet. But looking at valence bond theory, we see that there are actually two different kinds of bonds in that double bond. There's one sigma bond and one pi bond. Any double bond is one sigma and one pi bond. That's the only way you can get things to overlap and form two bonds between the same two atoms. Those pi bonds are generally weaker because that side-to-side overlap is not as efficient as the end-to-end, because it's kind of a stretch for everybody involved. And so we find that the pi bond is easier to break than the sigma bond. And this matches up with what we observe in many, many situations, that the pi bond will break and the sigma bond will remain intact. Lewis theory does not predict that at all. It assumes that they're equal. Let's look at the difference between single and double bonds. So here we have dichloroethane. We've got 2 carbons, and each carbon has 3 atoms bonded to it. There is a single bond between the 2 carbon atoms. So here we've got 4 single bonds. Those are actually going to make sp3 hybrid orbitals, and one's overlapping with hydrogen, another's overlapping with hydrogen, this one's overlapping with chlorine, and the 4th one is overlapping with an sp3 hybrid orbital on this carbon. This carbon has the same sort of arrangements with its 2 hydrogens and chlorine. This bond, being symmetrical around that bond axis, can rotate. You can spin this end around and around. And you could have the chlorines both at the bottom, or you could have the chlorine at the top. And it can just rotate freely. I'll bring back the model kit, and the model predicts that as well. They could spin. In a double bond, here we've got this sigma bond in the middle and the pi bond up here. If we try to rotate these, we're going to have to break that bond. It can't rotate. A single bond is like taking your index fingers and sticking them together, and you can twist one hand relative to the other, right? Double bond is like taking 2 fingers and touching them together, and now try to twist one hand relative to the other. It doesn't work because there's the 2 bonds there, and it restricts rotation. Good. Good, he's doing it. You should all get your fingers out and do it. It doesn't work, does it? Yeah, he's just trying to prove me wrong. Depends on how flexible and double jointed you are. Yes. Yeah, this has very significant implications. This double bond cannot rotate. And so there's actually 2 different versions of this particular molecule. There's one where the chlorines are on opposite sides of each other, like that. And then there's this one where the chlorines are on the same side as the double bond. And they cannot interconvert without breaking the pi bond. You can draw this one with the chlorine on the other side, but drawing it doesn't make it happen. It can happen, but it can just freely go back and forth. It can just spin and spin and spin and spin. These are different molecules. Well, they don't have, they almost have the same name. There's one letter different. This is ethene, and this is ethane. Yeah, very, very subtle difference. Any other questions about this one? Yes?
The ability to rotate enables them to do what?
It enables them to have different conformations, which different arrangements in space. And this is kind of getting into a little bit of organic chemistry. These molecules are actually going to have slightly different chemical and physical properties because they are not the same. The chlorines being on the opposite side of the bond or on the same side of the bond can affect the boiling point. It definitely can affect how they interact with other molecules in their reactions. This one, because it just freely interconverts, there's only one molecule. It just can twist around. And so we mostly see the effect of the double and triple bonds with the lack of rotation being significant, and this is really more like what most things are, that they can all just spin around. These hydrogen atoms can spin around too, and the chlorine atoms could spin around. Not that anybody would be able to tell that they were spinning around, but they could. Any other questions?
So they are stable or they are not stable?
They're stable. They're stable. The way this is drawn here with the chlorines on the same side, chlorine is a relatively large atom compared to the carbons and hydrogens. And so these are both kind of bulky, and so they're kind of want their own space. So we actually see that most of the time this chlorine is going to be on the other side because they just like to spread out. It's like kids in the minivan. Could they sit next to each other? Sure. Are they going to? Probably not. And if they do, you're going to wish they hadn't, right? Just spread out. Nobody sit in that middle seat. Just spread out. And so these guys are kind of bulky, and so they're going to spread out. And so this will rotate around so that this guy can be on the other side, and that's going to be a little more stable than this one. But these guys, they're stuck. They have no choice. They have to stay on the same side of this double bond. The only way for them to get around to the other side is if this bond actually breaks. And if any bond is going to break, it's going to be this one, because this one is weaker than the sigma bond. Other questions? Need fortification. These are different illustrations. Of course, I got ahead of myself, because I always do that. Different illustrations, same molecules. So there's the two carbons. This one has a hydrogen hiding behind, and this one's the two hydrogens in the chlorine. And these can freely rotate around that carbon-carbon bond. And so we can see the chlorines being on opposite sides. This is what they're going to prefer. See how big they are? I need to go on a diet or something. But they're just kind of big and chunky. Big and fluffy, maybe. They're fluffy. And so they're not going to necessarily want to be next to each other. And then over here with the double bond, we've got this one, which is called cis, because these are on the same side, and trans, because they are on the opposite sides. Like a transatlantic flight goes across the Atlantic, right? So trans is a prefix that means across. So these are across from each other. But they cannot interconvert. They are two distinct molecules. We can also make triple bonds using valence bond theory. So here again we have our standard orbitals, and we're going to take one s and one p and average them together. And so that is called an sp hybrid orbital, because it's one s and one p. And again, we don't like to write ones, so we leave the ones off. And these two guys are unhybridized. They remain the same. Messing with these requires energy. If we don't get enough back, we're not going to mess with them. It's not worth messing with these guys. Well, when we average one s and one p, we end up with these two hybrid orbitals. We have two orbitals that are degenerate, and they're going to arrange themselves in a linear form. They're going to be on opposite sides of the nucleus. They do have their little tiny lobe kind of sticking into the big lobe of the other one, but we're not going to worry about that. And then where are those unhybridized orbitals, the p ones? Well, they're where they always were. So this was the px that we hybridized with the s. So this is going to be along the x-axis. The py is still going to be here along the y-axis, and the pz is going to still be there along the z-axis. So they're perpendicular to this hybrid orbital. Draw the Lewis structure for acetylene. Well, that kind of is the Lewis structure for acetylene. I don't know who made these slides. Oh, I did. Acetylene, C2H2, is like this. There's no lone pairs. By making a triple bond, this carbon has 8 valence electrons, and this has 8, and we've got the octet rolled down. When we look at acetylene, we find that it has sp hybrid orbitals. What's going to happen here is the atomic orbitals of carbon are going to hybridize. We're going to take this electron and move it up. So let me draw that. Move that up there. And this guy is gone. That's pretty good. And then we're going to hybridize these two those become this sp hybrid, and then we have two unhybridized p orbitals that are left over. And so each of these carbons can form 4 bonds now. So here's carbon with its purple hybrid orbitals. sp, sp, they're linear because there's 2 of them, and that's what 2 things do. And here's the other carbon with its sp hybrid orbitals. One of those will overlap with hydrogen, the other overlaps with the other carbon. This is a sigma bond, end-to-end overlap. This is a sigma bond with hydrogen. This is a sigma bond. And then we have 2 p orbitals that are left unhybridized. And so the py can overlap side to side with the py on the other one. And the pz can overlap with the pz on the other one. And so this is one pi bond over here and back there. And this is the other pi bond. 2 pi bonds, 1 sigma bond, triple bond. Any questions? We saw in the Lewis model that elements in the 3rd period or below can have expanded octets. And valence bond theory explains this by including d orbitals in the hybridization. The energies of the 3d orbitals are similar to the 3s and the 3p orbitals. They're a little higher, but not that much. So they're in the same range there. So here we have standard atomic orbitals, 3s, 3p, and 3d. Well, if we hybridize the s, 3 of the p's, and 1 of the d's, how many orbitals are we going to get? Count them. 1, 2, 3, 4, 5. Right? 5. We get 5 hybrid orbitals, and then we've got 4 unhybridized d orbitals. We're not going to torture you with the pictures of all the d orbitals and how they would all combine. You can imagine that that gets kind of hairy. But we end up with 5 degenerate orbitals. How do 5 things get away from each other in 3-dimensional space? That's 4. Tetrahedron plus 1. That's awesome. It's bipyramidal. Okay, so a trigonal bipyramidal. So we've got this. This was the little girl with the tutu. Remember that? So there's 3 of them here, and there's another 2 here. Remember, these are hybrid orbitals now. When we looked at just regular atomic orbitals, this would have been 1 orbital with its 2 lobes. But these have a similar shape to those other hybrid orbitals, in that there's the big lobe, and then there's a little lobe. And so we're just looking at the large lobe. And so you get 5 things together. So here's a Lewis structure for arsenic pentafluoride. So arsenic is going to employ that sp3d hybridization to get 5 equivalent orbitals. Each of these can overlap with fluorine. And so we find that this explains the geometry of the arsenic pentafluoride molecule being trigonal bipyramidal. Why is fluorine making a sigma bond with its p orbital instead of an s orbital? Hydrogen did it with an s orbital. Fluorine's bigger. Let's look at the orbital diagram for fluorine. How many valence electrons does it have? 7. 1, 2, 3, 4, 5, 6, 7. The half-filled orbital that can overlap without hybridizing is a p orbital. So this is the one that's overlapping with the arsenic. Remember, we're assuming that these terminal atoms are not hybridizing. That's not strictly true, but that's what we're going with, okay? sp3d2. Well, we've got the S, 3 Ps, and 2 of the Ds. And we hybridize all of these together, and we get 6 degenerate orbitals. 6 degenerate orbitals are going to make this octahedral shape. And so each of these can form a sigma bond with one other atom. So here's sulfur hexafluoride. Sulfur will do the sp3d2 hybridization, and then it can overlap with each of these. Any questions? So how do we know what hybridization scheme? I guess it's kind of your question earlier. How do we know? How do we know if it's going to be sp or sp3 or sp3d2? Well, there's 2 methods. There's the rigorous method, which we're not going to do. That can be calculated. You can figure out all the different combinations and look at the energy, and you're wanting the one with the lowest overall energy. So we're not going to do that. Good enough for Chem 1A. This is what we're going to go with. We're going to assign a hybridization scheme based on the electron geometry of the interior atoms. So we're going to use Lewis theory and Vesper theory to help us predict the hybridization. It's not 100% accurate, but it's good enough, and it's so much easier. So it's kind of like, baby steps, right? And does everybody need to learn how to pole vault? No. Does everybody need to learn how to walk? Probably. So, walking is a lot easier than pole vaulting. Have you ever tried pole vaulting? It's hard. It's really hard. I tried it a couple times in junior high, and I was like, not for me. Not for me. Anyway, so the rigorous method would be like learning how to pole vault. I don't even want to do that. So we can look at, just like we learned on Tuesday, we can look at the number of electron groups and the geometry that is predicted from Vesper theory. And we're going to use a hybridization scheme that gives us this many orbitals. If we have 6 pairs of electrons, if we have 6 electron groups, we need to have 6 hybrid orbitals. You start with S, and you add 3 Ps, that gets you up to 4, so you've got to take 2 Ds. And you start with S, go to P, then D, and take as many as you need. If you've got 3 groups, you're going to have sp2. Does that make sense? That's not too hard. So list of instructions. First, you have to write the Lewis structure. Then you have to use Vesper theory and predict the electron geometry. Then you're going to choose the correct hybridization. You're looking at the number of electron groups, and you need that many hybrid orbitals. Then you're going to sketch the molecule. You start with the interior atom and its orbitals, and then show it overlapping with the appropriate orbitals on the terminal atoms. And then you label all the bonds, sigma or pi, followed by the type of overlapping orbitals. So this will challenge your drawing skills. Use valence bond theory to write a hybridization and bonding scheme for carbon dioxide. What's the first thing we have to do? Lewis structure. Lewis structure. So we'll put carbon in the middle, and we'll put 1 oxygen on each side. We're going to pretend we don't know what it is. How many valence electrons do I have to mess around with here? Carbon has 4, and each oxygen has 6. So 12 and 4 is 16. And we go 2, 4, 6, 8, 10, 12, 14, 16. We ran out. So we're going to make some double bonds. And that was helpful, but not quite enough. And so we'll take these guys off and move them in here. And we come up with this for our Lewis structure. How many electron groups around the central carbon? 2. 2 electron groups. What geometry will that have? Linear. That's a linear electron geometry. So we've got 2 groups. When we hybridize orbitals, how many hybrid orbitals do we need? To get 2 groups, we need 2 hybrid orbitals, right? So it's going to be sp hybridization. Can't spell. No, I was right the first time. Hybridization. Hybridation. Hybridation. SP. Now we're going to draw this. This will be fun. So we're going to start with the interior atoms. Well, in this case, there's 1. So there's carbon. I'm going to use color because I can. What are the sp hybrid orbitals going to look like? We're going to have 1 lobe for each, right? And they're going to be on opposite sides. So we're going to have 1 going over there and 1 going over here. Those are the sp hybrid orbitals. What does carbon have left? Let's look at a orbital diagram. 1, 2, 3, 4. Those are the atomic orbitals. And then we took 2 of them and made sp. And then these 2 guys are left, right? And they're each going to have 1 electron. So those are the p orbitals. So I've got 2 sp orbitals. I drew those in purple. I'm going to draw the p orbitals in red. So they're going to be perpendicular. So there's 1 up and down, and there's 1 coming out here, and there's 1 going back there. You just have to use your imagination a little bit. Now I need to put oxygen on there. So oxygen, there's going to be 1 oxygen over here. And what kind of orbitals does oxygen have that are half full? Okay, so down here is oxygen. It's got 1, 2, 3, 4, 5, 6 electrons. We're going to assume that it doesn't hybridize. So it's got these guys, right? So it's got 2 p orbitals that are not full. We're not going to draw the ones that are full. These have lone pairs in them, and remember we were pretending that lone pairs were invisible, so we're not going to draw those. So I'm going to draw 1 of these overlapping like this. What kind of a bond is this right here? That's a sigma bond. So I've got this orbital. Where do you think the other p orbital is going to go? It's going to be perpendicular. It can either be up and down or in and out. What do you want to do? In and out, just because we're hungry. So this orbital on oxygen could overlap with this guy, right? You see that? Side to side overlap. That's a pi bond. Now that oxygen has 2 bonds. 1 pi bond, 1 sigma bond. And then over here, we have the other oxygen. And he's got the same kind of orbitals, right? So he's got 1 that's going to come over here, and that one's going to go off the screen. And there we've got another sigma orbital. In order to overlap with that remaining carbon p orbital, how does this one need to be oriented? Up and down. So this will be oriented up and down, And these guys can overlap side to side. And then we're supposed to label these. I'll label them in maybe green. So this one right here is a pi, and the carbon has what kind of an orbital? An sp, and that's overlapping with an oxygen's what kind of orbital? P. And this bond over here is the same sort of a bond, isn't it?
Yes.
We've got... No, I made a mistake. What did I do wrong? I know, but I'm going to make you tell me. What kind of an orbital is this? If we're looking at this bond, I was looking at the purple one, but it's this red one, isn't it?
Yeah.
It's a p bond. Not a p bond, a p orbital. So that's pi CpOp. And then we've got, where can I put this? We've got this guy down here. What's that one? Sigma. And now we've got the sp on the carbon and what on the oxygen? Just p. Do we have another one of those? We did. Question?
Why do the p orbitals have 4?
They have 2 lobes. And so the one pair of electrons occupies both lobes.
So it kind of zooms back and forth.
Well, see, it's a wave function.
But the sp only have 1.
The sp, it does have a second lobe, but it's very small, and it's going on this side.
And we don't draw it.
We don't draw it. We ignore it.
They all have 2.
They all have them, yes.
But when they're hybrid, we only draw 1.
Right, because the one is so much larger, the other one doesn't really have an effect. Here, these 2 lobes are equal, and so they are equal in effect. These guys, this one is so small compared to this one that it just doesn't really matter at all. That's the glossing it over, don't worry about it explanation.
Sweet, okay.
Okay. See, we made it.